Bertrand Eynard he actually has two positions, but he's at the Institute of Theoretical Physics in Seoul, but also associated with CRM in Montreal. Okay, so he's going to talk about an overview of the topological recursion. Professor Eynard.
Hello, so good afternoon. Well, first I would like to thank the organizers of this ICM to have invited me here and given me the opportunity of presenting this talk. So what I'm going to talk about is an overview of topological recursion. Well, topological recursion is, you may guess, a recursion. One example of topological recursion is Mirzakhani's topological recursion. Mirzakhani got the Fields Medal last week. Probably, I don't know if you have seen pictures similar to that in Mirzakhani's work, but this is so Mirzakhani is an example of the topological recursion, but there is a much more general structure behind that, and that's what I'm going to talk about. First, what is all this about? What is it about? So, the topological recursion is it's an algorithm which produces something by recursion. What does it produce? Well, first it needs an input, and the input is what's called a spectral curve. I will give definitions later. But so, out of a spectral curve, by some recursion, the topological recursion produces numbers, which are often called FG, and it also produces some forms, a sequence of forms. So an infinite sequence of numbers and an infinite sequence of n forms. And those numbers and forms are called the invariant space. Well, I will give the definition later, but why is it interesting to have that? The definition that I'm going to give for this topological recursion, so when those invariants are produced, why is it interesting? Well, it's interesting because those invariants have many beautiful mathematical properties, like, I don't know, modular forms or things like that. I mean, many of the properties you like in mathematics are there. Another reason why they are interesting is because they have many applications. So many specializations of those invariants are some invariants which were known by other methods, like, I don't know, Gromov-Witten invariants. The hyperbolic volume, so it's what Mirzakhani's work is about. The node polynomials, so for instance, the Jones polynomials, and many other things. In fact, initially, the topological recursion was introduced in the context of random matrices. In random matrices, initially in the abstract which I gave to ICM, I was mentioning random matrices. But here, in fact, I'm not going to mention too much random matrices today because I have only 45 minutes. I'm giving an introduction about random matrices quite long. And also because Marianne Mirzakhani got the Fields Medal about the hyperbolic volumes, I will rather present my introduction with hyperbolic volumes. So quite different from random matrices. But the idea behind all this, so how this topological recursion was introduced, how the topological recursion was introduced, it's because when you study random matrices, and when you compute, when you want to compute large size asymptotic expansions, you realize that the coefficient in the large size asymptotic expansions do depend only on the spectral curve. So the larger limit of the distribution of eigenvalues. And they depend on it in a universal way. And the idea was to reverse the thing. So instead of having a random matrix problem find the spectral curve and find all the corrections. The idea was start from the spectral curve independently of any matrix model and define by the recursion, define some invariance for that curve. So somehow it's how probabilities gave something about algebraic geometry. So let me introduce this recursion by an example. And the example will be Mirzakhani's recursion. So let's consider the moduli space of genus G Riemann surfaces with n boundaries. So a Riemann surface with n boundaries on some genus. So MGN is the space of all such Riemann surfaces. And there is a set of local coordinates, which are called Fenchel-Nielsen coordinates on MGN, which are defined as follows. So those first, choose the hyperbolic matrix. Choose the hyperbolic matrix on your Riemann surface. So which is the matrix with constant negative curvature -1, and such that the boundaries are geodesics of fixed prescribed length. So this matrix is unique. It's the Poincaré matrix. And then cut your surface into pairs of points, such that the boundaries of the pairs of points are geodesics, are closed geodesics. And then the coordinates, so the Fenchel-Nielsen coordinates, are the lengths of those closed geodesics, and also the twisting angles, because when you glue two such geodesic boundaries together, so which are circle, you can rotate them by some angle. And so the set of angles and lengths, the set of angles and lengths are the Fenchel-Nielsen coordinates. But they are only local coordinates because there is not a unique way of cutting a surface into pairs of points, and here is another way with geodesic boundaries. Here is another way, so you get different lengths, different angles, but it's still the same element of MGN. So the coordinates are different, but what you can show is that the measure, so the volume form, product of DLI d theta I, so the top volume form, is in fact independent of how you cut into pairs of points. It's, and this is called the Weyl-Petersen matrix on MGN. So this allows to compute the volume of MGN. So you can, in this way you can compute the volume of MGN. Well, it's complicated to compute those integrals. It's very, very complicated. That's why, and what Mirzakhani has found is a recursion relation among those volumes, which really allows to compute them. So that she did that using using geodesics on in hyperbolic geometry, and that's really great work. Well, I also wrote another formula for those volumes, which is more algebraic geometry type, which involves psi classes are in fact chunk classes on MGN, and kappa 1 is the first Mumford class, so this second line is more for specialists who know what it is. Well, so I'm going to explain, to give the recursion to compute those volumes. In fact, I'm not going to give directly the recursion to compute the volume, I'm going to work in Laplace transform. So let me define the Laplace transform of those volumes. So you take the volumes, multiply by e to the minus zi li, and integrate li from 0 to infinity. That gives a function WGN of the zi's. Well, let me, so as I said, those volumes are not easy to compute, but let me give you some examples. Well, for instance, for M03, the volume is trivial, it's 1, and the Laplace transform is just this rational function. For M11, it's more difficult to compute, but the volume is that, and the Laplace transform is that. For M04, you can also compute the volume, and this is its Laplace transform. Well, observe one thing is that in each case, the volume is polynomial in the Li squares, and thus the Laplace transform is a polynomial in the 1 over the I squares. This is not an obvious fact. This is not, you cannot see it directly on this expression, it's the result of the computation, and for instance, it can be proved by the Mirzakhani recursion. Well, okay, so let me now tell you what the recursion is. So the recursion, so Mirzakhani's recursion is written in terms of the volumes, but here I write it in terms of the Laplace transform. So you've probably not seen that last week, that equation last week. You have seen the Laplace transform version. So, and also, so it's a recursion which gives WGN plus 1 in terms of over W with smaller genus or smaller number of boundaries. Also, in Mirzakhani's recursion, you have 3 types of terms in the right-hand side, whereas here I have only 2 types of terms. It's because, in fact, in Laplace transform, two of the terms can be put together by introducing W02, which is that. In fact, there is no V02. The volume of M02 is not defined. There is no hyperbolic matrix on cylinders. So the volume of M02 is not defined, but if you define this W02, then somehow you can simplify Mirzakhani's recursion. Well, so this is let me show you an example of computation with this recursion, just to show you that it's extremely simple to use. Let's compute the volume of M11. So let's compute W11, which is the Laplace transform of V11. So this is just the rewriting of the previous slide for M11. So if you choose G equals 1 and N equals 0, that's W11, equals here you get a W02, and here that sum is empty because of that constraint. You exclude all W01, so that sum is empty in the case of M11. So that's just the rewriting of a recursion. Let's compute it. Well, remember that I defined W02 to be 1 over z minus prime to the square. So this means that this term is in fact just 1 over 4 z squared. Now, since you have to compute residue, you just Taylor expand everything around 0. So this is the expansion of the first term, the expansion of the sine function, this 1 over 4 z squared. So the pi is going to cancel, the 2 times 4 is going to make an 8 times z0 squared. So let's put it in front. And so you have this, you have a triple pole and the expansion of the sine function, for instance, here. And so you put it in the numerator. So the residue of the triple pole is just the coefficient of z squared. So it's just going to be that term plus that term. So it's that. And you can check that this is the correct answer. This is the correct answer. This indeed is the Laplace transform of this V11, which was the correct one. So this is just to show you that the topological recursion is very easy to use in practice. You could do, you can do those computations by hand. So now let me show you that this topological recursion in this case is just an example of a much more general structure. So let's put the Mirzakhani's equation, which is here, in a universal form. So first, the z variables here, which came from Laplace transform, now instead of thinking of them as complex numbers, let's think of them as element of a certain Riemann surface. While here, in this case, the Riemann surface is just the set of complex numbers or the Riemann sphere, so if you have the point at infinity. Okay. The second step will be to turn the WGNs into differential forms on sigma to the n. So symmetric differential forms. So it's a tensor product of 1 forms in each factor. So in order to do that, you take this equation and you multiply by dz1, dz2, and so on. So multiply by dz0, dz1, and so on. Well, so here this is omega gn plus 1. But here, this is not yet an omega. To get an omega, so you have dz1, dzn, but you don't have the dz and the minus dz. Well, the dz is here, but the minus dz is missing. So what you do is, you multiply, so you put the dz here, you put a minus dz, but this means you have to put a minus dz in the denominator. Well, it may look strange to have minus 1 form, so with a dz in the denominator, but in fact it's because the numerator is a quadratic form divided by 1 form. The result is a 1 form, so it makes sense. So now this is an omega gn, so let's write it this way. So now we have done it with forms. Now let me see what this factor is. This 0 over c0 square minus c square. Observe that 2z dz0 over z0 square minus z square is that integral. And that factor is exactly what I called the W02, or I mean the omega 02. So integral from minus z to z of omega 02. So let's rewrite it this way. So let's write this term here. We have also a 2z, which is appeared here. Now let's try to see what are those terms. So let me introduce a function y of z, which is sine 2 pi z over 4 pi, and another function x of z, which is z squared. Well, so this is 4y, so this one is 4 times y, and this one is dx, the differential of x. dx, 2z dz is dx. So let's write it this way. In fact, because y is an odd function, instead of writing 4 times y, I prefer to write 2 times y of z minus y of minus z. It's because I will be interested later in curves which have no involution. So this one was odd, it had an involution, but for general curves there will be no involution, so I prefer to put things in that form. Alright. Well, now I also define omega 01 to be y dx, so that you can also write it this way, omega 01 of z minus omega 01 minus z. It starts to look more universal, but there is still something to understand. It's why we take a residue at 0, and why we have a minus z appearing in many places, minus z, minus z, minus z. So it remains to understand what are the 0 and minus z. Well, the 0 here, in fact, comes from the 0 of dx. dx vanishes at z equals 0. And so in general, instead of taking 0 here, I will take residue at the zeros of dx. And the minus z is such that x of minus z equals x of z, because x is even here. So x of minus z equals x of z, and in general, the function to which to z associated minus z will be replaced by what's called the local Galois involution. So which exchanges the values of z which correspond to the same x. So let's replace it. So let's write the recursion that way. So this is Mirzakhani's recursion, which I have just rewritten in this way. But now this is the universal topological recursion. So let me make it a definition, the definition of the topological recursion. So this is the general topological recursion. So the input of the topological recursion will be the data of a Riemann surface. So what I will call the spectral curve will be the data of a Riemann surface and two functions x and y on it. And also omega 02 will be a symmetric two-form on sigma cross sigma, which has a double pole on the diagonal and no overpole. Well, in fact, since I'm going to only compute residues, what I really need is it's not really a Riemann surface. It's only local formal neighborhoods at each branch points. So it's a set of local neighborhoods of each branch points. And what you need also is that y, you don't really need a function for y. You just need the germ of some analytical function, so some formal series at each branch point. That's all what you need to define the topological recursion. So it's much more general than having Riemann surfaces. But the case of Riemann surfaces has more properties, enjoys more properties. And then, it's just the same as the previous equation. It is the definition. It defines some omega gn by recursion. What is not obvious at all from the definition is that it is symmetric in the n+1 variables here. The z0 in the definition seems to play a different role compared to the other zi's, but in fact you can prove by recursion that you always generate something which is symmetric. Okay, so this is the definition. Just one more remark. In this way, I define omega gn for n at least 1. You're never going to define omega g0 with that definition. So I need a separate definition to define omega g0. It's given here. So omega g0, most of the time people call it fg. And omega g0 is obtained as follows. First, you compute omega g1 by your previous version, multiply it by the antiderivative of omega 01, take a residue at all branch points, divide by 2 minus 2g, and that's fg. That's the definition. Well, it's just so far it's just definitions. Well, why are those definitions interesting? Well, we have seen that Mirzakhani's recursion is an article case of that, so one specialization is Mirzakhani's recursion. I mentioned that those recursions also appear in the large size expansion of random matrices. But then, well, what can we say more about that recursion? So, one reason it's interesting is because it has many beautiful properties. Well, first, as I say, I call FGs on omega GNs, I call them invariants. Well, it's because they are indeed invariant under something. They are what I call symplectic invariants. So most of those properties which I'm going to mention have been derived in the paper where we introduced all those definitions in 2007 with my student Nicolas Aurentin. What do I mean by symplectic invariant? It's if you change x and y by a biration one, by a symplectomorphism. So if you change xy to phi1, phi2, such that the wedge form dx wedge dy, so the symplectic form dx wedge dy is conserved. So if you do that, then Fg is invariant. This is not obvious at all from the definition. It's the result of, the proof took us like 30 pages and it's not trivial at all. And also our proof is valid only if S is really algebraic. So if the curve is a compact Riemann surface with norm on x and y are meromorphic functions. We believe that this symplectic invariance holds in a much more general case, but so far we have no proof. Well, it has many other properties. Another property is that the FGs are modular forms. Well, if you are familiar with modular forms, you know that being modular is a very important property most of the time. So the fact that we always get something modular means that these are really nice objects, these FGs. I'm not going to comment too much on it. Another important property is integrability. Those FGs are related to an integrable system. There is a notion of lax pair, tau function, isomodulonic system, Hirota equations, and all that. Again, I'm not going to comment. It's just to say that these really seem to be interesting mathematical objects. Another very, very nice property, which is very powerful, is that it commutes with limits. I think that this could be called like Crepant resolution or something like that. It means that, for instance, if you have a family of spectral curves, which, for instance, tend in some limit to a singular spectral curve, then the FGs somehow go through the singularity in some sense, which I'm not going to detail, but it's really a beautiful and powerful property. For instance, in the context of matrix model, it shows you that if you are near the edge of a spectrum, you recover the expansion of the Tracy-Wheeldon distribution or things like that, here in a quite easy way. Another nice property is related to form cycle duality. Very often it's mentioned, it's called more like cyber-Wheaton or special geometry, but the property is the following. So if you want to make an infinitesimal deformation of the spectral curve, well, so basically you want to take a tangent vector to the space of spectral curves. In fact, it happens that the tangent space to the space of spectral curve at a point is the set of meromorphic forms on the curve, of meromorphic one form. So taking a tangent vector means taking a meromorphic one form. And it turns out, and also a meromorphic one form is dual to a cycle. And it turns out that the deformation of, so the derivative of omega gn in the direction of tangent vector omega is the integral along the dual cycle of omega gn plus 1. And again, that's a very beautiful and very powerful property. It allows to do plenty of things. It gives lots of relationships and all that. And there are many other nice properties. There is one property which I want to mention now, which makes the relationship to which makes the relationship to moduli spaces, and which will bring us back to Mirzakhani's recursion later. It's the following thing is that omega g, so for really every spectral curve, even those defined only by local formal neighborhoods and things like that, for every spectral curve, omega gn is always some integral over some moduli space of surfaces of G with n boundaries. There always exists a certain moduli space and a certain cohomology class in that moduli space, such that omega gn is the integral of a cohomology class over mgn. Well, this theorem would not be very useful if that cohomology class on that moduli space would be complicated. But in fact, they are very simple, and that's why this theorem is useful. MGN, in fact, this MGN is in fact just a combinatorial space. So it's represented by diagrams like that, of colored diagrams. There are as many colors as the number of branch points in the spectral curve. And in fact, the true definition of this integral over this MGN should be a sum of row graphs of some integrals in the standard MGN, so the standard moduli space of Riemann surfaces. But it's more, it would take more space to write, so I prefer to write it this way. But the important point is how to compute that cohomology class. So the beautiful property is that this cohomology class is always the exponential of a linear combination of Mumford's kappa classes, which are well-known objects. And so the thing we have to compute is the coefficients for the t hat case here. What are the coefficients of that linear combination? And it turns out that they are very easy to compute. And what you do to compute those t hat case is you compute the Laplace transform of y dx. So take y dx multiplied by e minus ux, integrate, that's the Laplace transform, so it's a function of u. And that function of u, you take minus the log, and you expand it at large u. And the t hat case are the coefficients of the negative powers of u at large u. That's all. So that's very simple to do. And this theorem is very nice. Well, let me say some comments. So, in fact, it was proved by Dunbarton, Orentin, Chadrin, and Spitz last year that this theorem implies that the omega gn always satisfies some Giventhal formalism. Well, not really always, in fact. It corresponds to Giventhal formalism only when omega 01 and omega 02 are related by a certain relationship, which I'm not going to explain here, but very often it implies Giventhal formalism. But in fact, the star theorem is more general. It holds even if there is no relationship between omega 01 and omega 02. But in some sense, people consider that it's more or less equivalent to Giventhal formalism. This sum of graphs is the same as in Giventhal. Another remark is that, what I've said so far is that, it's a mirror symmetry. On one side, we have a B model. So the spectral curve is what's called a B model, and the moduli space is what's called an A model. And in the B model, what we have is we have forms omega 01 and omega 02, and so the moduli of the B model are the moduli of the curve, they are the moduli of those forms. And on the A model, we have the moduli space, and the moduli are the coefficients in the cohomology classes. So they are the t hat case, basically. And the two are related by Laplace transform. So in some sense, you can say that mirror symmetry is similar to Laplace transform. And many other authors have claimed that, but here it's quite explicit. Let me show you how to apply this theorem in some special case, in particular in Mirzakhani's case. In Mirzakhani's case, so let's choose our spectral curve, so sine 2 pi 0 4 pi, that's y, x is z square, omega 02 is that. Well, in that case, there is only one branch point, and our moduli space in that case, this combinatorial moduli space has only is graphs with only one color, and in fact there is only one graph in the sum. So basically this MGN is just the usual MGN, the moduli space of remote surfaces of GNG with n mark points. And it remains to compute the Laplace transform. So let's take integral of y dx to the minus ux. We replace y and x by their values here. And you see that in the z variable, this is just a Gaussian integral. So it's extremely easy to compute. So, and it's just here the result. So it's just a Gaussian integral. And now if you take the log and expand at large U, you find that there is only U to the minus 1 with the coefficient pi square. So it means there is only t hat 1, which is our pi square. And it means that our cohomology class is just exponential of pi square kappa 1. But it is well known that exponential of pi square kappa 1 is the Weil-Petersson form. So the product of ELI dθ in differential unit coordinates. So in fact, by using this star theorem, we have proved that the topological recursion applied to that curve produces the Weil-Petersson volumes, produces the volumes of moduli spaces. So in fact, we have proved Mirzakhani's recursion by using this theorem. So, and you see, the most difficult part of the proof is just to compute that Laplace transform somehow. Well, I mean, if you have already proved the star theorem, of course, before. So you see, it's quite easy to use. Let me show you another example. Let me take that curve. Well, you may wonder why to choose that curve. If you write y as a function of x, this is the so-called Lambert function. And it appears in on the Lambert function, for instance, it is the generalizing function for trees, I think, for trees, and it's equivalent also for the generalizing function of Hurwitz numbers of genus 0, of simple Hurwitz numbers of genus 0. But so let's compute the Laplace transform. So the Laplace transform, again, is extremely easy to compute, and it's the gamma function. It's the gamma function of minus u. And again, if you expand it at large u, you have a steering approximation of the gamma function, which involves the Bernoulli numbers. So pk is the kth Bernoulli numbers. And so the coefficient, so here is the t hat k. T hat k is b k over kk minus 1. And so this means that our class, the cohomology class, is this exponential with those Bernoulli numbers times the Mumford's kappa class. It turns out that this precise combination of Mumford kappa classes is well known. It was computed by Mumford, but it is the Hodge class in the moduli space. So what we get is that if we start with that spectral curve, what we get is that the omega gns are Hodge integrals over mgn bar. And this is this thing in the right-hand side is exactly the right-hand side of the famous ELSB formula. And here again, we obtain it just by doing this three-line computation. So it seems to work very well. Another example is if you take that curve here. That curve is known in algebraic geometry as the mirror of C cubed, which is a very simple Calabi-Yar manifold, the most simple Calabi-Yar manifold of dimension 3. So again, compute the Laplace transform. Well, it's quite easy. You get the Euler beta function, which involves three gamma functions. So again, you do the large U asymptotic expansion of the log of that. Again, you get some Bernoulli numbers. In fact, the same Bernoulli numbers, but with three terms here, corresponding to the fact that the class, our class here, is now a product of three Hodge classes. So again, by using this star theorem, without much effort, what you get is that the omega gns of that curve, so which is the mirror of C3, is a combination of triple Hodge integrals. And those triple Hodge integrals are the Gromov-Witten invariants of C3. Sorry, they are the Gromov-Witten invariants of C3. So what you prove somehow by using this star theorem is that the Gromov invariants of C3 are the omega GNs of the mirror of C3. This is a special case of something much more general, which was first conjectured by physicists like Marcus Marino and his collaborator, which was called the PKMP conjecture. Well, basically, the PKMP conjecture in 2008 was the claim that the Comor-Fruiten invariance of a Calabi-Yau threefold, of a toric Calabi-Yau threefold, equal the omega Gn of the mirror of that Calabi. This is what we can also prove with this star theorem. So it was proved last year, in 2012, with my student Oranta. So take X, semi-projective toric Calabi-Yau threefold. It has a mirror, and the mirror is typically a curve of that form, polynomial of e to the x to the y equals 0. I just showed you the example of C3, but let me show you another example, x equals local P2, so which is certain Calabi-Yau. Its mirror is this polynomial. It's a genus 1 curve, which means that log x and log y are elliptic functions on the torus. So, you apply the star theorem, which means you have to compute those Laplace transforms, and you have to do some combinatorics, which is not so trivial, but you have to do some combinatorics, and after doing some combinatorics, you get that the omega GNs of that curve equal a certain sum of our graphs, and at each vertex of the graph you have a triple Hodge integral, and it turns out that this is exactly the Comor-Fruiten invariance of x. That's more or less how they are defined. So what you prove, so this proves the PKMP conjecture. This proves that the Comor-Fruiten invariance of x equals the omega Gn of the mirror of x. Okay. Let me go to other examples. Very recently it was realized that another place where those invariants play a role are in knot theory, for instance related to Jones polynomials. Well, choose a knot, for instance here this is the figure 8 knot, one of the simplest hyperbolic knots. Well, every hyperbolic knot has a character variety. The character variety is given by a polynomial equation. Here, this is the example of a polynomial equation for that knot. It's not difficult to derive it, and character varieties are known for every knot, basically. And so it's now take it as the spectral curve. So take it as the spectral curve for our knot. One thing people are interested in knots is their Jones polynomials. Well, the Jones polynomials, the color Jones polynomials, is a polynomial in some formal variable q, so it's a polynomial in q, but which depends on an index n, which is called the color. The usual Jones polynomials is with n equals 0, or n equals 1. Yeah, well, and what people are interested in is the asymptotic expansion of the Jones polynomials. Well, the asymptotic expansion in the regime where q goes to 1 and n goes to infinity, but such that n of q remains finite, so call it u. Then you want to compute the asymptotic expansion in the following form. So take the log of a Jones polynomial, expand it into powers of log q in that way, and the coefficients are named sk of u. And so the question is, how can you compute the coefficients sk of u? First, it's not easy at all to prove that every Jones polynomial for every knot has such an expansion. It's not proved in general. And the second thing is that even just computing the leading term is a conjecture. It's the famous volume conjecture. And the conjecture is that the leading term, so the S0, is the so-called volume. Well, it's the volume of the knot complement in S3. But even that is not proved for general knots. It's proved only for basically just a couple of knots. It's not proved in general. So proving that such an expansion exists for all knots and computing the SK for all knots is still a very big challenge. But there is a conjecture for that. Well, so far the conjecture was concerning only the leading term, but now there is a new conjecture saying that for all terms in the expansion, so for every k, SK of u is a very simple combination of the omega GNs of that curve. And so in particular, if you take it for k equals 0, this is the integral of omega 0, 1, and this is the volume conjecture. But so the conjecture says that this is true for every k. So maybe it will help in proving the volume conjecture, I don't know. But so far, nothing of that is proved. It's conjecture. You can check it numerically to very high orders, for given knots, but it's still a conjecture. But it shows that the invariance omega gn, so the topological recursion, plays a role in Jones polynomials. But it's not at all understood why. Well, another example I can mention is about the problem in combinatorics, counting 3D partitions. So a 3D partition is basically you put cubic boxes in the corner of a room, and at random, we were going to consider random partitions. But here let me take a room which has itself corners. So there is, I don't know, chimneys in the corner of the room, and you put cubes. When you put a lot of them, so in the large size limit, you get something like that. You can get something like that. Very large number of them. And observe one thing. So, sorry, yes, the colors don't appear. I'm sorry. Well, observe one thing. There are some regions here where there is no cube here. Okay? Or here, for instance, here. There is no cube reaching the wall here. And what you can see is that there is a kind of limit shape which separates two regions. There is a flat region here, which is called frozen. So there is also a frozen region here, and so on. And here, there is a region where you really have disorder, and it's called the liquid region. The curve which separates the liquid region from the frozen region is often called the Arctic circle. Because if you started with a room with no corner, it would really be a circle. And so it's the Arctic circle. It was a famous work by Kenyon, Okunkov, and Sheffield to show that this limiting curve, so in the large size limit, is the algebraic curve of the smallest degree, which is tangent to all boundaries. So in that example, it's a cardioid. And so now what you are interested in is to compute, well, correlations. So you take random partitions uniformly in this large size limit. You take random partitions, and you are interested in computing correlations, expectation values, and all that. And in particular, you want to compute the partition function, so which is just the sum of all configurations in the large size limit, and you want to compute asymptotics of that. And for instance, for the partition function, if you take the log, you expect an asymptotic expansion of that type, so the size to the odd powers, and the coefficients, call them fg. And what are they? How to compute them? And it's a conjecture that those coefficients are the fg, defined by the topological recursion, applied not really to this curve, the Arctic circle, but applied to its Lagrange transform. So it's a conjecture, and it's more or less proved for some shapes, because this partition function is in fact the Donaldson-Thomas invariant of certain Calabi-Yau three-folds, and also Okunkov and collaborators proved that those Donaldson-Thomas are equivalent to Gromov-Witten invariance, and since we have proved the thing for Gromov-Witten invariance, somehow it proved that this conjecture holds for at least certain types of shapes. So let me conclude my talk. So what I've shown you is that the topological recursion can be used to define some invariance of a spectral curve, and this definition is a computational definition. Well, physicists would say it's a good definition because it's computational, but probably mathematicians would say it's a bad definition because it says how to compute things, but it does not say what it computes. So, that's a challenge to really understand what we are computing this way. So what we see is that this topological recursion is universal. There is no parameter in the recursion itself. It's totally universal. And there are many problems in enumerative geometry, in round matrices, in combinatorics, in knots, etc., which satisfy the same recursion, exactly the same recursion. The only difference is the initial data. So it can be used as a unifying framework, but also it's amazing why is it so universal? Another reason why you can be interested in that topological recursion and in those invariants is that they have fantastic mathematical properties. Like just finding modularity is very interesting by itself. Integrability also is a very beautiful property. And as I said, so there are many applications. So for instance, Gromov invariants are a specialization of these, the volumes of moduli spaces, but you find it also in Hitchin system, in the asymptotic expansion of Hitchin systems, and many other things. But proving that those programs to satisfy the topological recursion is most of the time a challenge. So for instance, proving that Gromov invariants are the omega GNs of the mirror curve was a conjecture for many years, and it was proved only 1.5 years ago, and it was considered a really difficult problem. And also the proof is technical, so it means that the proof does not explain why it's true. It's just a technical proof, and we have absolutely no geometric understanding of why it is true. Somehow we don't have what Mirzakhani found for volumes of moduli spaces. We don't have a Mirzakhani's decomposition. So what we need is to be able to understand how to generalize Mirzakhani's work, to really understand. Well, so just the topological recursion can be pictorially represented by this way. So we know that omega Gn computes some integrals over some mgn, so basically it computes some numbers of such surfaces, and the topological recursion says that it's equal to another number of surfaces. But we don't, so somehow there should be, so the topological recursion seems to imply that there should be a canonical decomposition of surfaces not into pairs of points, but things which look more like those red pieces. So the red piece here is more what I would call a short. So it's a pair of points but without the legs. So that's what the topological recursion seems to imply, but we don't know. So it seems to imply that there is such a decomposition, but except that we don't know what is this decomposition. And it's a big challenge to really understand if that picture has a geometric meaning. So I would like to thank you for your attention.
Thank you, Professor Eynard, for such an illuminating lecture with such a rich content. We now open for question and comment, but before that, the organizer has a question for you. Okay, so questions, comment? Yes.
Well, it could be that to derive the topological recursion in some generality, I mean, one approach could be to make rigorous, say, the definition of the topological string in terms of worldsheet CFT. Because in a way it seems that it has the right structures then. So infinity structures.
Well, I don't know. As I said, this would correspond to somehow this would correspond to having, so if you already have worldsheets well defined, you can expect to be able to foliate them in some way, but in fact, even in the cases where we really have well-defined worldsheets and well-defined theory, even in that case, we don't know how to foliate it in a way which looks like that. So I think, just for instance, just to compute the number of what mathematicians call maps, or what physicists call discrete surfaces, or rebounding graphs, just to compute the number of rebounding graphs which are discrete objects, so well-defined discrete worldsheets, we don't know such a decomposition. So we can prove topological recursion holds, but the proof is extremely technical. It's very far from having a biological proof.
Yeah, so many years ago, I guess 20 years ago, Eguchi and his group were using random matrix models to represent Gromov invariants, and it feels like this method supersedes their work or interprets it. Is that a fair point of view? Or?
Well, yes or no. Well, indeed, there is such, the idea, well, when we wanted to prove this BKMP conjecture, so proving that the Gromov-Witten invariants do satisfy the topological recursion, since the topological recursion was invented as computing the asymptotic expansion of the matrix model, of course we thought that if we have a matrix model for Gromov-Witten invariants, this would immediately imply that this conjecture holds. But no, it's not that simple. Because computing large-size asymptotics of matrix models is extremely difficult. First, just proving that there exists an asymptotic expansion is already very difficult. Proving, well, basically finding just the equilibrium state of the eigenvalues, it's kind of solving a saddle point approximation. The problem with those Eguchi-type models is that there is a very large number of saddle points. Just proving that the good one is the mirror is just by itself extremely difficult. So, I mean, this was the obvious idea we had at the beginning, and in fact, this is the reason why Marigno and others made that conjecture. It came exactly from there, but it was just a conjecture. Proving it was difficult, and so our proof does not use the matrix model. It uses only combinatorics on this start theorem.
We have another question from here.
So, what are you computing in the Hitchin system case?
In the what, sorry?
Hitchin systems.
In Hitchin systems, what you are computing is the coefficients of the WKB asymptotic expansion.
That's great. Maybe we stop here. Thank you again.